Hello guys, today we go into the part 3 of reinforcement learning, and in this part we'll talk deeply about the most conventional algorithm about reinforcement learning, which is the Q learning table. And before going to that, I will summarize what we've learned on part 2. The first one is about the flow of the agent. So as you guys know that the agent that based on DP, the policy in here, they get the data from the state, the previous state, and then based on the policy, PS, they give some decision like the action A. And that action will interact with the environment, and the environment in return will send back two signals. The first one is about the state of the environment, what is the environment being changed, and the second one is about the reward, is it a good or bad action. So based on the reward, the agent will fix the policy in here. Okay, so the flow is kind of simple as I draw in this board here. The first one, the P of S, they based on the state, they based on their knowledge, you can know it as a knowledge, they give some action A, and the action will interact into the environment, and the environment will send the reward, which reward will be used to fix or update the P until it reaches the P star. Yeah, we repeat 1 and 2 until the P reaches into the P star. Okay, so that's the goal of the reinforcement learning agent. And for the policy, we have two types of policy. The first one is about deterministic policy, which means like whenever they see the state, they will always choose the action A no matter what. And the second one is that stochastic policy, which means like there's a possibility. For example, if they reach the state S, this agent could give some kind of possibility like 50% that I will go up, 25% I will go down, 24% I will left, and 1% I will right. Yeah, they pick the action based on the possibility. The goal is like we need to find the optimal A, the P star, right? The policy star. So for the reinforcement learning method, we have two types of method: the value based or the policy based. I will go deep into it later, but from now I will talk deeply about the value based that could be our prioritized. Okay, so as you can see, like from the state, they pass it into the agent, right? And this agent, depending on the state, they will give some kind of action. There are 4 possible actions: up, down, left, and right, for example. And each one, they will do the action, interact to the environment, and then the environment will send back again the reward, right? The state and the reward, and each action has its own reward, right? 10, 20, 15, and 11, right? So in order to, we need to have some kind of question. So we have a reward, but reward for what? We have two types of reward. The first one, we reward just based on the state only, which means like if S1, S2, the state are all the same, right? But the action that causing into the state, for example, on S1, the position is kind of like 2, 1, right? This is the action, this in here. But on the S2, the action is over there on the 1, 3, 1, 3, 2, 1, right? Two actions, they are different, but the state, they look really similar, really the same. So we reward two things kind of like the same. The second type is that we value it differently if the action that causing the state different. For example, we have to say here like, I'm sorry I missed this one. Okay, it's kind of like the same in the above, but the difference is that in the first one, the x, you can see in the x, this is the action causing this state S1, and on the S2, the action is caused from different location, 1 3, right? On the 1 3, so we value to Q differently because the action that goes into the state different, so that's why we value differently. On the first one, the VS1 and VS2 are the same, but on the second one we value the Q different. So in this flow, in this session, we will follow the action value QSA. Okay, we don't care about the VS, or you can research it by yourself, but on my course I will teach only about the QSA. Okay, so that one here, so we have the question like, like the ZT, the expected reward, as I mentioned above, like the expected reward is calculated by you just play the game, play it non-stop until the end, right, to get the reward, because you don't even know is it action good or bad until you play it until the end using your policy to play it. So you use it, you will use this one. Let me mention you that a little bit. The gamma is kind of like the value, like as more far away, they will value down this reward, because like it's not important, right? The more close the set is, the more important it is. But if it's too far, there's no matter. So okay, going back, so we have the Z, we have the expected reward as I mentioned above, right? So we will value this one using the reward for what? Reward for the state causes by the action. This is a formal formula, but you just remember this one, this is way easier. Okay, you can imagine it like this, like on P will, it is a state, okay, and this is the agent, and the agent for the P, they do some action H, they go to the state S, they do some action H again, they do the ST plus 1, ST plus 2, and it gets a list of reward from the RTS1, RTS2, and so on, right? They calculate all the reward and total together to get the total value, or aka the expected reward. So yeah, this one means that we value the state and also the action that created that state by the total value. Okay, so yeah, this is the basic foundation. On the next one, I'll talk deeply about the algorithm. This is the first conventional algorithm that people created, that's the Q-learning table. They imagine that they have the table, that you can think the table as a policy. It's a policy. It's not actually a policy. I'll show you that it's not actually a policy. Okay, we'll talk about the Q-learning table. For example, we have the game in here. Yeah, this is the mouse, this is the player, and this is the goal. And our goal is that to let the mouse eating the pizza. Is it a pizza? I don't know. Eating the. Our goal is to let the mouse, let the player move this one, right? Eating the cheese and reaching the goal to get the highest score. Okay. And as you can see, we have the table in here on the right side, and in this position, the mouse can only go right or go down. If the mouse go right, they will reach the state like a bomb, right? So the Q bomb right, the Q bomb right is -5, and the next one is the down, right? Q down. If he goes down, he will reach the empty. So the Q empty down is 2. So which one will you choose? You choose the one that has the best value, best reward, right? So you will choose this one. Go down. So that means like the policy of the S is equal to max QSA. We have a list of QSA and we will choose the max. So it also means that if you need to find the optimal policy, P star, we don't change this max function, we couldn't change it, but instead we need to find the optimal QSAs, right? Finding the optimal policy P star, which means we need to find the optimal QSA. So from the QSA, as I mentioned you above, the QS is actually the expected value onto the state that was created by the action 8. So we have the list like here, but that raises some kind of question like, so it means like we need to play it into the end for just one step. For example, if the mouse move like this one, just one step. In order to calculate the expected reward, we need to like play it into the end to get the reward for just a step, right? We calculate it all until the end. Reward. Yeah, we calculate all until the end just to get the reward for one step. So that's kind of unrealistic, right? So we need to find another way to avoid that unlimited loop. And yeah, just it's kind of like the time consuming. So why don't we just simplify that long? So the Bellman say that that's simple, but we just like use recursive function like dr t plus 1, we will keep it, but for the get drt plus 2 or t plus 3 and so on, why don't we just reuse this q as t plus 1, a t plus 1, that's it. So what is just the meaning of it? There are two different meanings. The first one, we can use the recursive memorization so that like we will go from here down to the end, we calculate this reward. The next time when we train, we have that reward data, so we don't need to go step by step once again. We'll feed it back to the mouse. And also the second one is way more optimal. It is we can reuse data in the Q table, because like the QSA, this one, we will just collect it directly on this table, right? The table has all the data. We need to collect this one, put it into it, and we just calculate RT plus 1 and we will get the QSA. That we will follow this one, the second one. So one question, how to optimize the QSA, right? Because like as I mentioned above, we need to calculate the optimal policy, which means we need to calculate the optimal QSA. So how to optimize it? So as you guys remember, in neural network we optimize by using the loss function. The loss function, which means like we need to calculate the distance between the prediction and the ground truth to see the difference, and we fix it, right? And also in Q learning table, it's kind of the same. We will optimize by, I don't know how to say it, but I will call it a delta. It means like we need to calculate the difference between what you predicted and the ground truth. Predicted it means like the data on the table, and the ground truth would mean like the action that the agent interacts with the environment to send back to the world, which is the ground truth, so that we can update the Q learning table. So in Monte Carlo, he said like in order to update it into the new data, we need to use the current data, and we change it based on the loss within the delta, the difference between the prediction and the ground truth. Yeah, the current and the ground truth, you see. Yeah, and we see like how wrong is the prediction, so that we could plus it into the current to fix it to get it better. And in this one, we have the alpha in here. It's kind of like the learning rate on the reinforcement on the neural network. But like as I mentioned above, like the Q router, it is this one, right? It is this one. They will continue play until the end to get the router's data. And also, as the Bellman said, like we just use recursive function to short it down so that we can reuse the data from the Q table, and that's it. So boom, that is a sample difference learning, which means like Q new is Q current plus the alpha, the learning rate. The learning rate, this one is a whole Q router. The Q router, we can expand it like the RT plus 1 plus the gamma QST plus 1, blah blah blah. Yeah, you can understand like this. It's just like the router minus the Q current. It's just like that, but they trying to expand and apply the Bellman formula to short it out. So overall, the Q learning algorithm, we have some kind of steps like this. The first one, we need to initialize the Q table like this. We use some random number, yeah, or some kind of we set up by manually. Maybe we inherit from other data so that we just update it. Yeah, but overall it's just random. Random is the most common chosen. The second one is about we need to let the agent play the game using their own policy. They use based on the state, they use the policy and they give some action. And the formula, as I mentioned you, is the max QSA, right? We choose the function, the action that give us the most reward, yeah, that give the most QSA. The third one is update the QSA. As I mentioned, how to update the Q new is kind of like we let the Q current we update it plus it is update. This one is a learning rate, and this one is let the routers minus Q current to get the loss. Okay, and we just repeat the 2 and 3 multiple times to get so that the Q table update time by time to read until the Q star, right, at the point when it's good. But how to determine whether it's good or bad is kind of complicated topic. I'll tell you guys later, but from now this is the algorithm of Q learning table. Okay. Oh, on the next part, I will talk about the limitation of the Q learning table. So why don't they use it nowadays? What's the limitations and how can they fix it? How can they apply neural networks for the Q learning table? As I will mention it in the later part. Thank you guys for listening.